Okay, hey everyone. So this is Ken 430 Process Design 1, Lecture 5, Week 5, and the next few lectures will be short ones. So maybe next 4 or 5 weeks we're going to have shorter lectures so that you can start retaining more of the Aspen Plus simulations. You can spend more time working on your projects and other things. So in this lecture, we'll start talking about sequencing ordinary distillation columns. And before we kick off, a few announcements. This week 5. September 21st, sequencing ordinary distillation columns and Aspen Plus tutorial number 4 will be added this week. Aspen tutorial number 3 is due, and you have 2 weeks to submit it. And please start working on your projects. Start finding communication paths with your group. Start, setting the tone for your group, setting the workflow, and start working on your projects, because this is where you're really going to make most of your learning. Tackling a problem, trying to take decisions, looking for the solutions, and this is where most of your start building your experience. Okay, so let's start off. So the objectives here is to understand how distillation columns are sequenced and how to apply some heuristics to narrow your decision making when trying to find a sequence, right? You also need to be able to apply systematic methods to determine the optimal sequence for distillation type problems. So let's get started. So if you recall from last week, talked about a concept which you also cover in mass transfer called the separation factor. And your separation factor, you said it defines the degree of separation achievable between two components in the feed. So look at this diagram here. If I have feed, component 1, component 2, entering into a distillation column, and I separate it in two phases. My top phase, which is vapor, my bottom phase, which is liquid. And each of these phases is a mixture of both, right? In most cases, you don't get this pure, perfect, cute separation. Both of them are mixtures. So in phase 1, which is your vapor phase, I have component 1. I'm writing it as C1I, component 2, C2I. And my bottom phase here, I have also component 1, C1II, component 2, C2II. And your separation factor is calculated using this equation. C1I divided by C2I over C1II divided by C2II. And it gives you an indication on how easily these two components can be separated. Okay, and again, we talked about how you can use mole fractions to represent these components, and you can also calculate your separation factor. And y1 over x1 is called k1, y2 over x2 is called k2, and you will see this a lot in your mass transfer course. And alpha 1, 2 becomes your relative volatility. And K1 and K2, you can refer to them as your vapor-liquid equilibrium ratios for both components 1 and 2. And alpha 1, 2 is your relative volatility. Okay, so two things you need to be aware of. The larger the value of the separation factor, the more feasible the separation is between components 1 and 2. So the larger the alpha is, the easier it is to separate these two components. It's also important to remember that even though, this K1 and K2 are temperature dependent, pressure dependent parameters, right? So if I increase my temperature significantly, of course, it's going to be easier to separate two mixtures, right? Or if I increase my pressure significantly, of course, it's going to be easier to separate two mixtures. But you always want to calculate your alpha values at non-extreme conditions, right? So you want to be realistic when making your assessment for designing your separation trains. Okay, you can also calculate your volatilities using the vapor pressure, saturation pressure as follows. So, if you don't really have this information, or you're not sure, or your information is in some sort of format which favors vapor pressure, you can use the vapor pressure to calculate. So saturation pressure of species 1 over saturation pressure of species 2 will give me my relative volatility. And again, for non-ideal liquids, as we said before, the vapor pressure might not, or as your liquid deviates from ideality, the vapor pressure stops being as accurate, because now you have the chemical nature of the species starts playing a role. And that's why you have the fugacity and activity coefficients, and they're basically corrections to account for the chemical nature of the species when calculating vapor pressures. Okay, so more non-ideal it is, I have to keep an eye out that, okay, maybe if I use vapor pressures, it might not be as accurate as I want. Okay, so how do you sequence your distillation columns? So usually, as we said in the last lecture, if I have multi-component mixers, I would need more than one distillation column, right? So last lecture, we talked about propane, butane, mixture of butenes, and we had like 8 different columns to separate them. So similarly, and this is called a sequencing decision, right? Which one should I separate first? Which one should I separate last? All of this stuff. So these are sort of like things you need to keep an eye out for when sequencing your distillation columns or your ordinary distillation columns. The alpha, or the relative volatility, should be greater than 1.05, which means this separation is feasible. If I'm separating 2 components and I calculate the relative volatility and it's 1, or it's less than 1, or it's less than 1.05, then this separation will not work out, right? Due to many factors, both thermodynamic, operational, realistically, it's not going to work out. Your reboiler duty should not be excessive, right? So again, you should not be operating at extreme conditions. You should not be operating at conditions that require you to input significant amounts of heat for this process to work. The tower pressure should not cause the mixture to approach the critical temperature of the mixture. And again, similarly, you want to avoid operating at extreme conditions. You want to avoid operating at critical conditions. Your pressure drop has to be tolerable, especially if you're operating under vacuum. And this decision, and this you might not really be able to gauge it at the very early stages. However, as you move on, you should be prepared to make changes in your decision making if your pressure drop is so high. Because a high pressure drop correlates to very high operating costs and also correlates to higher maintenance costs and other things. The overhead vapor should be at least partially condensed at the column pressure to provide reflux without excessive refrigeration requirements. So this is similar to point number 2. You don't want your energy requirement of the column to be very high, whether it's at the reboiler at the bottom or at the condenser at the very top. The bottom temperature, again, of the tower should not be so high so that chemical decomposition occurs. And 6 is sort of going back to 2 and 3. You don't want your temperature to be so high that you either reach your critical point or you reach a point where the molecule starts breaking down and you start getting a lot of impurities or new species which you don't want to deal with in your process. Okay, and of course, azeotropes. You want, if you can avoid having an azeotrope or moving from one side of an azeotrope to another side of an azeotrope in your distillation column, you should always do this, right? And if you remember from your Aspen Plus tutorial, if you want, you can have 2 distillation columns, one operating on one side of the azeotrope, the other one operating on the other side of the azeotrope, but you don't want to have, always want to avoid having this crossover occurring in one unit. Okay, so in order to determine the number of distillation scenarios you need, and you need to use this equation. So the number of different sequences of ordinary distillation columns, and this is referred to as NS here, to produce P products is determined using the following equation, right? So if I want to separate P different components from each other, I use this equation to determine the number of possible sequences which you can use, right? So if I have A, B, C, and D, I can separate A first, I can separate B first, maybe I can separate A and C first. You can see there are many different ways to do it, or many different possibilities. And it's just if you want to use a stable, if I want to separate 2 products, 1 separator is enough. If I want to separate 3 products, 2 separators is enough. And now it starts deviating, right? If I want to separate 4 products, I need 3 separators, and NS becomes 5. I want to separate 5 products, I need 4 separators, and number of sequences is 14. I want to separate 6 products, I would need 5 distillation columns, and I can arrange these distillation columns in 42 different arrangements. And if you have 8 products or 7 products and you want to separate them, you will need 6 and 7 distillation columns, but I can arrange these distillation columns in 130 ways, 400 ways. And obviously one of them is the best way to operate, right? One of them is the best solution considering economics, considering operational parameters, considering many other factors, right? So it's something to keep in mind that you always have a bunch of options, and decision making will depend on multiple factors. So for example, if I have 4 components, I want to separate them. I can separate, if I have A, B, C, and D, I can separate A first and separate B, and separate C and have D at the end, so 3 columns. Alternatively, I can separate D first, then separate C, then separate A and B, or I can, maybe separate A and then separate D, and then, a bunch of different ways to do it, right? So again, here I have 4 components, I need 3 columns, I have 5 different sequences to do it, right? 4 products, and I need 3 distillation columns to achieve this, and I have 5 different possibilities to achieve this objective. Okay, so how do you select the best sequence? You have some heuristics, right? So you need to use the following guidelines, and this slide will be important. So on your exam, you'll probably get a bunch of multiple choice questions. I give you a bunch of sequences, tell you which one do you think is the best, right? You need to use these guidelines to guide your decision. Okay, number 1, remove thermally unstable, corrosive, or chemically reactive components early in the sequence. This is somewhat intuitive, right? If I have a chemical that's thermally unstable, corrosive, a chemical which you're not just going to do something, or it might react or something, get rid of it as early as possible. Just remove it as early as possible, and make your life easier. Remove final products one by one as distillates. So ideally, you want to remove your products, your final products, as distillates, right? And this is called the direct sequence. And by the direct sequence, I mean this. So it's always better to remove your the products you want from the top of the column as distillates one by one. This is as opposed to the complete opposite, which is I'm removing them from the bottoms here as condensates, right? So just something to think about. Number 3, sequence the separation points to remove those components of the greatest molar percentage in the feed. And this is important, right? You always want to try to remove the components with the highest flow rate in your feed first. Because if I have a feed which has 70% of component A, I want to get rid of component A or separate component A as early as possible. So because this will make my units smaller later on, right? And this will save me a bunch of capital cost, a bunch of operating costs, and that type of thing. So number 3 is very important. Considering 1 and 2, of course, you want to remove the component with the greatest molar percentage as early as you can. You sequence your separation points in the order of decreasing relative volatilities, right? So that the most difficult splits are made in the absence of other components. So as we said in the earlier slide, relative volatility gives you a gauge at how easy this separation happens. The higher the relative volatility, the easier the separation. So you want to sequence your separation in the order of decreasing relative volatility, right? So you want to the components with the highest relative volatility, you do the separation first, and then the more complex separations, you do them towards the end, right? So you want to do the most difficult splits in the absence of the other components. We have 2 components where the relative volatility is 1, for example. I want to separate, I want to leave these to the end, and then I can deal with these by themselves. Maybe use another technology or something, whatever it is. Make your easiest separations first. And again, sequence separation points to leave last those separations that give the highest purity products. So you want to sequence your separation in a way that you can get the highest purity, right? And this says last, this is number 5, so you don't just jump to this. you need to make sure you satisfy 1, 2, 3, 4, and then the end. This is more applicable to cute, easy cases, but in more complex cases, this you might never have to deal with this. Okay. Sequence separation points that favor near equimolar amounts of distillate and bottoms in each column. The reboiler duty should not be excessive. And number 6 has more to do with the way you design and operate your distillation column. So if I'm separating two components, I don't want my distillate flow rate to be 50 times higher than my bottoms flow rate, right? So we're basically just boiling everything out. I want it to be, I want it to operate in a balanced way, where I have a bunch of products and a bunch of bottoms as well, right? So this goes back also to point number 3, where you try to eliminate your heaviest component first, or the component with the highest molar percentage first, and you leave everything else at the bottom. So this way, now at the bottom I have a good amount. I can also have a balanced column next, a balanced column next as well. Okay, so this is an exercise where you have a feed with propane, isobutane, N-butane, isopentane, and pentane, a bunch of hydrocarbons, a couple of them are very close, right? 2 pentanes, 2 butanes, and you're being asked to design a sequence of ordinary distillation columns to meet the given specification. And your specifications are, I want a 98% propane, 98% of every other component, so I want to separate these 5 components out of each other. Okay. First step is always to get your relative volatility between your component pairs, right? And the way to get the relative volatility, or the way to calculate the relative volatility, is arrange them by boiling point, right? So C3 has the lowest boiling point, and C4, and C4, IC5, and C5, right? So C3 by IC4 is my relative volatility, IC4 by NC4, NC4 IC5 is the relative volatility, and finally this is the relative volatility. So again, first step, you arrange them based on your boiling point, and these are already arranged based on the boiling point. Then you calculate the relative volatility for each adjacent pair, C3 IC4, IC4 NC4, NC4 IC5, IC5 NC5, and I write my relative volatilities here. And once you get to this point, this will give you some information about how you should move ahead with your separation. So in this case, 3.6 is much higher, so 3.6 is much higher than the rest, so this is an easy separation. 2.8 is much higher than the rest. This is an easy separation as well. I have a bit of a hard separation here, 1.5. It's greater than 1.05, so it's still feasible, and 1.35 greater than 1.05, so it's still feasible, right? So let's move on. So guided by heuristic 4, the first column in position to separate the key components with the greatest separation factor. So again, if you recall heuristic number 4, you need to sequence my separation points in the order of decreasing relative volatility, right? And if we go back to our heuristics, thermally unstable, corrosive, none of them are thermally unstable. Final products 1 by 1, this will be achieved, right? So as much as possible, try to get a direct sequence. Sequence separation points to remove those components of greatest molar percentage. Okay, we might have to think about this, and then sequence separation points in order of decreasing relative volatility. So why did we go to 4 and not to 3? Because if I look here, propane is 45, butane 136, 226, 181, 317. Why didn't I just remove M-pentane first? You didn't remove M-pentane first because you want to maintain your sequence to be as direct as possible. So I didn't remove M-pentane first because I want to remove them 1 by 1 as possible, and I need to maintain a direct sequence. So why don't I remove N-butane first? Well, seems that separation between N-butane and isobutane and N-butane and N-butane and isopentane is easy. However, N-butane and isobutane is not that easy. But I already have a very easy separation here at the top, and it will also satisfy heuristic number 2, right? Where I'm going to remove one of my products, first of all, as a distillate. So if you weigh these two options together, it makes sense to separate C3 first. This is what we did. Just first step, highest relative volatility, I took out C3, and then I'm going to follow this logic to do the next separation. So next separation I'm doing the separation of the second highest relative volatility, which is 2.8 between NC4 and IC5. And then I get IC4 and NC4, alpha is 1.5, IC5 and NC5 alpha is 1.35, right? So in this case, I followed the logic of, doing the separations in order of decreasing relative volatility. And this, at this point, this is a feasible design because it satisfies the heuristics. It's not violating any of the heuristics in a very major way. And, the columns all are balanced. Maybe this column is a bit unbalanced. I have a lot of C3 and a lot of bottoms, but in the bigger picture, this separation is so much easier than these guys that it makes sense to just do it at the beginning. Okay, so let's move on. In some cases, complex rather than simple distillation columns could be considered when developing a distillation sequence. So sometimes, let's say IC4 and NC4, the alpha is 1 or 0.9 or something like that. So distillation might not work. So I need to look for another technology to achieve it. And this is what this point is saying. Sometimes you need to do complex rather than simple distillations. Again, you can use direct sequence, indirect sequence. These are what we talked about. So direct sequence, I'm just removing my desired products from the top one by one. Indirect sequence, I'm removing my products from the bottom one by one. Could have, something like this. Distillation with vapor side stream rectifier. So I have a big distillation column with a second distillation column, and the second distillation column recycles back to the first one. Liquid side stream stripper, similarly, but this recycles to the top, this recycles to the bottom. So you can have some complex designs for distillation column. And you see this a lot in oil and gas refineries, where, if you extract crude oil, it has 60 different components and you want to separate them. You have aromatics, you have oxygenates, you have all types of junk in there. So now your decision making, you need to make some tough choices, right? And again, there are a whole bunch of types of things. And this is a reference paper where he discusses the different options if you're interested to read. Okay, so when simple distillation is not practical and I need to use other types of separators, the order of volatility or other separation index might be different for each type of separator. So you just need to remember that the relative volatility separation factor, which we talked about earlier, this is only valid for ordinary distillation. If you're using another technology, you need to be aware of the other parameters which are valid for that technology. We're only going to cover ordinary distillation, but I think in mass transfer, you're going to talk about absorption and stripping and liquid-liquid extraction as well. So you could you could get that information from that course, okay? So in the cases where I'm using two product separators, and if T equals the number of different types of separation technologies, the number of sequences is now given by this, right? So if you're using more than one separation technology, you need to adjust your number of sequences using this parameter T to the power of P minus 1, okay? So now, because you're using multiple technologies, your number of possible choices, number of possible sequences increases by a lot. And this is the way to calculate the updated number of sequences. So for example, if you have P equals 3 and ordinary distillation, extractive distillation, either solvent 1 or 2, and liquid-liquid extraction or solvent 3 are to be considered. So I have one technology, and then the second technology is extractive distillation with either solvent 1 or 2. So these are two different technologies, and liquid-liquid extraction, solvent 3. So this is my fourth one, T equals 4. So a number of possible sequences now becomes 4 to the power 3 minus 1 multiplied by my original number of sequences using only one technology. Okay, oops, let's go back to our example, butene's recovery. So this was from, I think this is the same one from the last lecture where I have propane, 1-butene, N-butane, trans-butene, cis-butene, and N-pentane. is N-butane, and I want to separate them to get propane, N-butane, a mixture of butenes, and N-pentane. Okay, so we're gonna follow the logic we talked about this lecture in doing so. First of all, I'm gonna arrange my components in order of boiling point. So propane, lowest boiling point, all the way to pentane, highest boiling point. And what I'm going to do next, what you should do next is calculate your relative volatilities. And if you calculate your relative volatilities, you're going to find out that, sorry, let's go back to the equation for relative volatilities quickly, just to see it. So relative volatilities uses your vapor pressures, right? Yes, uses your vapor pressures, use your per liquid equilibrium ratios, which in this case is not provided, right? So in this example, if you're stopping here at this slide, take a minute and calculate the relative volatilities and verify that the sequence shown on the next slide makes sense, right? It does make sense, but take a second and just go through this exercise. And this is how you would sketch it basically. And what we said is we're gonna separate the one C3 and one butene first. So propane and one butene, you'll find out that the relative volatility here is very high. This one, so A separation from A from B and E from F will have the highest relative volatilities. D and E, B and C will have the second highest, and then C and D will have very close or a very low relative volatility. And this is what guided the separation logic. I separated C3 and one butene, and then I separated propane and one butene. Pentane was withdrawn as bottoms. We said that these two cannot be separated by ordinary distillation because alpha was very low, less than 1.05. So we had to use a second technology, which was extractive distillation, or liquid extraction. We did this, and then we did a final one to remove the 2-butene. Okay. So go through this exercise, calculate the relative volatilities, see which heuristic was used to guide this decision making, and verify if it makes sense. Okay. And if you have any questions, of course, just come to office hours and we'll talk about it. So continuing to talk about the butene's recovery. So in this case, we use two different types of technologies. So T was equal to 2, which is ordinary distillation and extractive distillation. We have 4 products. We said propane, butane, butene's mixture, and pentane. So our number of possible sequences was 40, right? However, when we were designing our sequence, we didn't actually separate all the butene mixtures as one. We did 2 separations, right, for butene. We did 2 separations for butene where we separated the one butene by itself, and then we separated the 2 other butenes by themselves. So our P is actually 5. So in order to achieve what the prompt wanted, we had to separate the butene as 2 separate products and then mix them later on. So realistically, our number of products was 5 and our number of sequences was 224. So if you're doing this assessment and you find out that, I have 40 sequences or I have 200 sequences, you need to reduce the number of sequences that need to be analyzed. And in order to do this, you follow sort of a process of elimination. So you try to eliminate infeasible separation and enforce ordinary distillation for separations with acceptable volatilities. So if you're doing your preliminary assessment, you find out, 200 sequences, where do you start? You start by eliminating the ones which don't make sense at all. So let's have a look here. Propane, butane, pentane, but 1 butane and 2 butene are structured very different. So optical isomers are very closer. That's why we had to do it over 2 steps. Okay, good. So if we look at the relative volatilities of these guys, So as we said, propane and 1-butane have a very high relative volatility. Butene and M-pentane have also a very high relative volatility. And these two splits in the middle, one of them is barely feasible and one is not feasible at all, right? So splits A and B and E and F should only be done using ordinary distillation because they're so easy. Ordinary distillation should be sufficient. I shouldn't have any problems. C and D, which is this guy right here, is infeasible by ordinary distillation. B and C is feasible, but because this relative volatility is so low, maybe if an alternative works better, I should consider it, right? And this is what guided this decision making, where we said if we use furfural as a solvent for extractive distillation, it will increase the alpha to 1.17, and which or increase this split CD to 1.7. So 1.7 is significantly higher than 1.03, so I'm going to consider this split instead of using ordinary distillation. So the splits to be considered and all other splits forbidden. So I'm going to look at, so if you look at your sequences, I'm only going to look at sequences which have A and B and E and F, right? Any sequence which does not do these separations, I'm not going to look at them, right? So if a sequence tries to blend A and C and then have A and C, or a sequence tries to get A and E and B on the side and separate A and B, they're junk. Forget about them. So A and B, E and F, and then B and C. So any sequence which achieves B and C, I should also consider. Any sequence which considers A and C, I should also consider. Any sequence which considers C from B using the second technology should be considered, and any sequence which considers C and D from using the second technology should also be considered. So if I consider these splits and I forget about all the other splits, so I'm not looking at any split which tries to do C and D using ordinary distillation. I'm not looking at any split which does not achieve E and F. I'm not looking at any split which does not achieve A and B, even though it's mentioned A and C here, but this is sort of a weak argument for it. So, I mean, you can eliminate the processes that don't do A and B and you'll still end up with the right choice. So once I only consider these splits, I'm going to narrow down my number of possible sequences to a relatively small number, maybe 5, 6, 7, maybe 10. And then once I narrow it to the small number, I need to look at other factors, primarily economics, to make me decide which one is the best sequence. And we're going to talk about this next week in the next lecture. So this is it for today. Thank you so much. Please start working on your projects. If you have any questions about your projects, come and see me. Just try to establish your synergy within the team. Try to establish an understanding on how you want to work, how do you want to do the deliverables, all this stuff, because this will be extremely important for your success in this course. And if you want to schedule a group meeting on the side, email me. We'll schedule meetings. I can schedule a weekly meeting with each group if you need to. Just start working on your projects. Thank you very much.